So I had a few of you ask about this question right here, and in fact this was the question people voted on for me to create a video for, so that's what I'm doing now. So in this case what we have is we've got a box that has a mass, and it's being suspended by these three cables, and because these cables aren't all in alignment with one another, we have to consider this as being in R3, and our goal is to find the forces in each of these cables. So I'm going to walk through this slightly differently than the way my math lab has you work through it. And the first thing I'd like to do is let's go ahead and label each of these as points. So I'm going to call this point down here Q, and I'll call this point P1, this point P2, and this point P3. Okay? Now if we were thinking about a force diagram on this box, what we would imagine then is we would have, here's the point mass that represents the box, and we would have the force due to gravity pointing downwards, and that force due to gravity would be the vector 0, 0, 100. That's our force due to gravity on this box. Now here you're going to see the limits of my ability to draw this, but imagine we've got the three different force vectors all pointing up at the various the various fastenings on the ceiling where this box is hanging from. And so I'm going to label each one of these. This will be the force vector F1 in the back here. This one will be F2. This one will be F3. And so because this system isn't moving, we know that the sum of all the forces on it needs to be 0. So we would have that F1 plus F2 plus F3 plus the force due to gravity needs to equal the 0 vector. Folks, careful, that's the 0 vector. That's the vector 0, 0, 0, not the number 0. So a force vector, the force in this cable, and we're representing it, say, like for this one, F2 here, the force in this cable right here, we're having it emanating, it's kind of a tension that's counteracting the force due to gravity here. And it's a vector, and so what does it need to have? It needs to have both a magnitude and a direction. The magnitude is going to be the magnitude of force, so just some quantity like 300 newtons or something like that, or in this case I guess we're measuring in pounds, so 100 pounds or 200 pounds or something like that. But it also has a direction. And although we don't know the magnitude of any of these force vectors yet, we do know the direction that they're heading in. And so that's what I'm going to set up first. So I'm going to say, and let me scroll down here slightly, perhaps, there we go. So I'm going to say that for force 1, that first force vector, that we could think of that as the magnitude of whatever that force is, but then we're going to multiply it by the direction vector, and here's where I differ a little bit in my explanation. I would rather not think of the vectors coming from P3 to Q. I'm going to go ahead and say that it's going to be this vector pointing in this direction here for each one of these. So this direction here. And then what that means is that when I'm done with this problem and I go to enter it into my math lab, I'll have to change the signs on the vector. I'll have to make sure it's pointing in the opposite direction. And by the way, that just reminded me, I've got an error here. This should be down here. Oops. This should be the value negative 100. Okay, so this for P1 here, which is this one right here, it's got some magnitude, which we're calling the magnitude of the force vector 1, but it's going to, as far as direction is going to be concerned, it's going to be the same as the unit vector that corresponds to this direction right here. So I'm going to go ahead and call that P1, but I want it to be a unit vector, so we'll divide it by its magnitude. So I'm using P for position because I'm talking about a positioning vector. And what is P1? I'm thinking of it as I drew this green arrow here. I'm thinking it as the vector that goes from Q to the point P1. So that's that vector right there. And now I can think of this in terms of the traditional tip minus tail. And so this would be the vector negative 4, comma 0, comma, and then this, careful, this would be 0 minus a negative 2 square root of 5, so that's a positive 2 square root of 5. So folks, if you want to see how I did that calculation, there's the component y's, where I took negative 4 minus 0, 0 minus 0, and 0 minus 2 square root of 5. Now again, because I've got these vectors pointing this way, if I were to be answering the question in my math lab, I'd have to change the direction of that vector. Now we can go ahead and compute its magnitude. So the magnitude of P1 is just going to be the square root of -4 quantity squared plus 0 squared plus 2 square root of 5 quantity squared. And so that gives us the square root of 16 plus, and that would be 20. So we get the square root of 36, and that gives us a magnitude of that vector of 6. So what I can now do is I can actually describe this first force vector in terms of some unknown magnitude. We don't know what F1 is. And in fact, I'm going to let, just for simplicity's sake, let's let A equal F1, just so I don't have to keep writing this as a vector. And so this would be the force vector. So let's see here. We had -4 was the first component divided by 6 times, so that would be -4a over 6, comma. Then this would be just, I'll go ahead and write the whole thing out, 0a over 6, comma, and then 2 square root of 5a over 6, where I went ahead and actually computed this. So I used a for this number here. Then I've got this vector, and I'm dividing it by the quantity 6. So each one of those terms got divided by 6. So hopefully you see where I got that vector from. And I'd like to just go ahead and reduce it down, because we're going to have to solve some equations with it. So this would be minus 2a over 3, comma 0, comma square root of 5a over 3. So just to clarify what we've done here, if you were to plot this vector and put its tail at this point right here, it would be pointing in the same direction as this cable right here. But the problem is we don't yet know what the magnitude of that will be, and that will correspond to the tension in that cable, the number of pounds of tension in that cable. We won't know that until we solve for A. But what we need to do now is we need to create a force 2 vector and a force 3 vector. So I'll go ahead and do that, but I won't talk through it as I work through it. So folks, what I've done here is in each one of these cases, I thought of our force as being the magnitude of whatever that force is, which we'll later call B or C appropriately, times a direction vector. And I got the direction vector. I needed to be a unit direction vector. I wanted it to be that. So I got the unit direction vector by looking up at, and those were supposed to erase on me, by looking up at the original image and saying, okay, well, for instance, for force 2 here, the direction vector is going to be the same direction as this vector that goes from Q to P2, and so that's how I got the coordinates for that direction vector. So for F2 there, I got the direction vector, and then I divided by its length, which also came out to be 6. All three of these came out to have a length of 6. That's unique to this problem. That won't always be the case, but oftentimes it is because you evenly disperse the cables. But it didn't have to be that way. So in each case, I thought of the force vector as being its unknown magnitude times its known direction, and there's that known direction vector. And then I just went ahead and let B or C or A represent that unknown magnitude, and I distributed that through. And now what I have is I've got three sets of unknown vectors, each one having one unknown parameter, either A as above or B or C like this one here. So let's return to our original idea where we said we want the sum of the forces, these force vectors, to be the zero vector here. What that means then is if I can add up the x component of this force plus the x component of this force and this force and this force, when I add up all of their x components, it has to come out to be 0. Likewise, when I add up all the y components of each of these forces, it has to come out to be the coordinate 0. And when I add up all the z components, it has to come out to be the coordinate 0. And so what we get is three equations, which I'll give here. So the first equation is negative 2/3 a plus 1/3 b plus 1/3 c needs to equal the number 0. This is the summation of the forces in the x direction. And how did I get that? If you go back and you look at these three vectors that we've built, here's the first vector, and I took its x component, and here's the second component, and I took its x component, and here is the third vector, and I took its x component. Oops, and folks, I'm missing something here. It's not going to make a difference in the answer, but I really can't forget. We also had the gravity component, so I'm going to put plus 0 needs to equal 0, and that's in the x direction. And this is because if you look at fg of x, that was the number 0. If we go back to that gravity vector right here, its x component is 0. So that I needed that as well. So those are the three forces in the three cables, and then there's the x component in the gravity force vector. And their sum has to give us the coordinate 0 for the summation of all the forces to come out to be 0. Likewise, we'll get two more equations, and I'll write those here. And so you can see here I've built these three equations. Again, for the second equation, for the y coordinates, I simply took the y coordinates of each of these three vectors, 0, this one, and this one, as well as the, so there they are, first A, B, C, those three y components, and then the 0 in our gravity vector, and that has to equal 0. And then for the last one, again, we've got this component plus this component plus this component, and this is where you got to be careful, plus the negative 100, which was the component in the z direction of our gravity force. Again, let me just show you that one more time. There was that gravity force, so there's that negative 100. And those three must also sum to be 0. So folks, all we have at in this point is a system of three equations, three unknowns, and I'm going to go through and solve that. So the first thing I'd like to do to help with solving that is let's number these. Let's call this 1, this is 2, and this is 3. From 2, because that component's 0, we see that we see that B must be the same as C. So if we plug that information into the first equation, so hopefully you see that if I added this over and then divided by the square root of 3 over 3, that would just give me the statement that B has to equal C. That's what I get from equation 2. If I plug that information that B and C are the same into 1, what I would get is, let's go ahead and replace the B up here with a C. I would have that A must be equal to C. So at this point, we know that A must equal B must equal C. Folks, this is related to the fact that these three cables are all sort of symmetric in the direction that they're pointing in, and have the same length, and so they're all going to have the same tension in them. You might have been able to make that conclusion from before, but I think this is the correct way to do it in a more complicated situation. So at this point, we know A is equal to B is equal to C, and if we plug all this information into the third equation, we'll be able to solve for those quantities. So if I do that, notice this is going to give me, if these are all equivalent here, let's go ahead and replace them all with A's, we would get that just the square root of 5A needs to equal 100, so taking that 100 over the other side, and so we get A is equal to 100 over the square root of 5. And that's what B and C are. So now what I'm going to do is I'm going to take these three vectors that I've come up with, this vector, and this vector, and I'm going to replace all of the variables, A or B or C respectively, with the number 100 over the square root of 5. So previously we had said that our force 1, that this vector right here was the vector negative 2/3 A 0A, comma, the square root of 5 over 3A. That's what we'd said before. And so if I replace all of those with the value A is equal to 100 over the square root of 5, what we'd get is if I replace, so if I put in a 100 over the square root of 5, I would get minus 200 all over 3 square root of 5, comma, this is still going to be 0. And then this would be 100 square root of 5 over 3 square root of 5, so the square roots of 5 cancel, and I just get over 3 here for that component there. And now I've got this force vector. Now, that answers the question, what is that force vector in that first cable? However, this is how we chose to orient it, and we thought of, remember, we thought of all these forces as branching outwards. When my math lab asks you for the question, though, they're going to want, let's see, they called this one force 1 here. They're going to want the vector pointing this way. So all you have to do to get the answer my math lab wants is to change the direction of that to 200 over 3 square root of 5, 0, minus 100 over 3. Now we've got the exact same vector but pointing in the opposite direction. And that's what we would enter into my math lab. And you can do that for the remaining 2 forces. So this one was the force vector 1/3 b, comma, the square root of 3 over 3b, comma, the square root of 5 over 3b. And then I'm just going to replace the b with 100 over the square root of 5. And I can compute that. I'm going to go ahead and leave the problem here because this has gone on long enough. But hopefully that gives you some insight as to how to tackle this question. Folks, I did find this an exceptionally challenging question. It was the last one I asked you. And if you're struggling with it, please don't worry. What I would encourage you to do instead is just make sure you understand the other problems up until this one and think of this as sort of a challenge or an extension question. There's a lot to juggle in it. If you do have any questions over this, though, please let me know. I'd be happy to give you more of an explanation during office hours. And I hope this video was helpful. Thank you very much.